Hi everyone, and welcome to the section 5.5 video on the substitution rule. So we are now in a stretch of the class with a couple sections in a row learning rules for integration. And so it should be very similar to what in Calc 1, you learned derivatives, you got a couple under your belt, and then it was like, okay, let's do a bunch of rules. It's going to be similar to this. So right now in your little toolbox, maybe it's not so little, your toolbox of derivatives and antiderivatives, you have, remember, a bunch of functions that you have memorized what the derivative is. Okay, derivative. But remember, you also then immediately have a toolbox full of functions here, f primes, that you know the antiderivative. Because remember, they are opposites, they go backwards. You take the derivative to get to f prime, you take the antiderivative to get back to f. So just the fact that you know a bunch of these derivatives tells you a bunch of antiderivatives. So you have this huge list of them that you already know. Okay, so that's a great start. The next thing we need to do is figure out how to use that for more complicated looking problems. Okay, so we're just going to jump right into this to kind of like think through what's going on here. So basically what we're trying to do here is we're saying to ourselves, all right, I'm looking at this and I want to do the antiderivative. Okay, that's the integral. I'm trying to find the antiderivative of this. Now, I don't have anything this complicated in my toolbox, right? But if I can think of this as, again, a composition of functions, get me an inside, right, and then an outside function, then I can simplify this using the substitution rule. And so here's the process you're going to follow. You write down what u is. Remember, just immediately go back to this rule. Let's go back up here. U is supposed to represent what's plugged inside, this g of x. Okay, so write down what u is. So you're going through here, what's plugged inside? I got this x squared, that's not really inside a function, that's kind of one of our basics. I'm over here, okay, well, yeah, this is like something to the ninth, but there's something extra in here. I found it. Whenever you say, like, oh yeah, there's this something extra, you've got a good chance that that's your u. Okay, now we have to identify this g prime as well, right? So it's not just f and g inside. We got this g prime here too. And so the way that we usually handle this is you write down u, then you immediately write down du. Okay, I'm going to show you kind of the idea of where this is coming from. This is not technically perfect, but this is the idea. Take the derivative of this. You get 3x squared. Okay, and now, just because we're doing this shorthand, we can move the dx over. Again, very technically unsound, but the idea is right. So what we end up with is u is this, du is this. And that's the whole point, right? Remember, I want to turn this into an integral with just u's, simplified. Okay? So let's do a substitution now. Let's take this information, go up here, and substitute. All right. So what do we got? We got this x cubed plus 5. That's just u. Okay, we got this 9. Okay, that's there. Now, it's a little trickier to see, so we're going to color code this. We have dx and x squared. So you're like, I got to get rid of that. Where do I see that? Oh, it's right here. Okay, that's good. But there's this 3 here. Oh, what do I do? So what we can do is we can take this 3, that's extra, because it's not in the integrand, right? And I'm going to divide it over. So what eventually is this going to give me? Just to kind of write it out so you can see it again. This really is the same thing as du over 3 is equal to x squared dx. Now guess what? X squared dx can become du over 3. I have no more x's, and look at this integral. Wow, that's a lot simpler. So I'm going to take the 1/3 out, and I know how to do this antiderivative. This is definitely in my toolbox. Add 1, divide. Don't forget your plus c. And then u was a dummy variable. Sorry, u, but it's true. U is a dummy variable that doesn't mean anything to us. So we need to go back to x's. 1/3 x cubed plus 5 to the 10th over 10 plus c, your first substitution. Sometimes this is called U substitution as well, so just be aware of that. And let me make sure I can get all of this in. Okay. So that's the format. So what's your procedure? Write U, then write du, try to pick out this inside function, take its derivative, then go match up all the pieces. Make sure that you can do a substitution here which gets rid of all the x's. You might have some extra constants lying around. That's fine. Just move them away if they're not in here. But they tag along, and that's okay. Constants are fine. So there we go. We've got it. Okay, let's try another one. Let's bring this one up. All right, so this one we're looking at, and maybe you're looking at this like, I can just do this. And it's true, you could probably think through how to do this antiderivative without U sub. But looking at this, my immediate thought is, oh yeah, sine t, right? Well, no, it's not sine t. Not quite. It's sine pi t. That's different. It's a different function. So we got to think like, oh, darn, we're so close. I need just this to be sine t. Well, I'm seeing a function and then a function inside, so why don't we just give substitution a shot? U equals pi t. Du is, take the derivative, just pi dt. And let's do some kind of trying to matching up here, right? So I see I can do a substitution, and this becomes U. Awesome. dt, where's that? Right there. Great. I got this pesky pi it's not out here. It's not next to this dt. It's not out here. But that's okay. Works the same as before. Divide, divide. All right, so let's do our substitution. Let's actually rewrite this out so you can see it a little bit better. So this, and this are going to combine to give me the integral sine u. And then remember, dt becomes du over pi, which is just 1 over pi, okay, the integral of sine u du. And again, this is in our toolbox, right? We got to just remember our toolbox. So this is equal to 1 over pi negative cosine u plus c, which, remember, I don't care about u, I want the other variable, so do the substitution back. Cosine pi t plus c. All done. Did I not zoom over enough? There we go. Maybe each of these, the box will get progressively closer to the side and off. That'll be fun. So all right, there you go. Set up your u, find your du, substitute, do the integral, plug back in. Let's try another one. E to the x cos e to the x. Holy moly. Get out of here with this function, you might be thinking. Well, just relax a minute. Let's think about this. I see a function plugged into another. That's your thinking. Do I see a function plugged into another? Yeah. Let's let u be e to the x. All right. Du. What's the derivative of e to the x? Oh yeah, that's just e to the x. Okay. Now just try it. A lot of this is about pattern recognition and just trying it. You're not always going to pick the right u. You run into a roadblock. Not all the x's are gone. You get you get a new integral that's too hard to do. You try something else. That's okay. That's going to happen to you a lot while you're doing this. So let's do the substitution. Remember, u. I'll come over here. Integral. Now I always like starting with this, the composition. You don't have to, but I like doing it that way. Cosine of e to the x is u. Okay. And then remember, we got to get rid of this dx. So we just go now find dx. dx is, oh, there. Ooh, but there's an extra ex here. Oh, I got one right here. Cool. So that all becomes du. And there it is. All right. What's the antiderivative of cosine? Sine. Now again, I don't want u's anymore, right? Give me x's. I can do that. Boom. And do not forget, you can always take the derivative of this to see if you did it right. Do a little chain rule here. Derivative of sine is cosine. Cos e to the x times the derivative of e to the x is e to the x, and bada bing, I'm right there. All right. Let's keep going. Let's keep trying these. Wow, giant space. Why is there such a big space? All right. Square roots, trig, y. It's okay. Composition of functions. Let's see if we can find one function plugged into another and just see what happens. Just trust your gut. Give it a shot. These substitution problems, there really shouldn't ever be a I can't even start. Just pick something to be u. Take its derivative and see what happens. You just go. So u is root x, which just for convenience, we're going to rewrite with the 1/2 power. Du, take the derivative, drop it down, subtract 1. Okay, so you're like, oh, okay, but what's going on here? And don't forget your dx. Well, let's rewrite this. 1/2, and then this negative means I can go to the bottom. But then remember, the 1/2 power is square root x. And a square root x on the bottom. Look at that. Yes. So feeling pretty good about that. We got this extra 1/2, but we know what to do. Get rid of it. Right? Get it out of there. And then what are we going to do? We're going to take this, this, and this, and we're going to put it all together. Why am I even drawing an arrow? You know where it's going. So we've got the integral of sine u. Okay, what's down here? Well, remember, and I know sometimes this messes us up with our algebra, but we've got the square root x on the bottom, and we've got a dx. I've got a square root x on the bottom and a dx. That's going to combine to become 2 du. Okay, so that's going to combine to become 2 du. And that, look, the bottom got absorbed away. So there's no more bottom. Look how much we've simplified that. Okay, put parentheses around here. So the 2 can come out. Remember, constants we can pull out. And then I'm just back to regular old sine. Okay, do the antiderivative. Negative 2 cosine u plus c. Okay, give my x's back. I don't want no u's. And there we go. Boom. So hopefully you can see how crazy looking I can make some of these, and they're just like, pick the right u, you're good to go. Whoops. Okay, let's keep going. Let's maybe kind of back up a little bit here, give myself some more space. All right. Look at this one. It's big. Look at how many. There's so many plus signs. Find a function inside another. This one looks like maybe it could be because of the parentheses, but there's no power here, so there's nothing extra really going on. I look here. Oh, look at that. I've got something plugged into something else. So just, you're going to build a little intuition, and then you're going to just start trying stuff. X cubed plus 3x. Do the derivative. 3x squared plus 3. Okay. All right, so, we might run into a roadblock here and have to start being a little creative. Okay, but let's just say, like, okay, we're feeling pretty confident. Let's go and see what happens. So we get the integral u to the 4th. Ooh, nice, okay. And then you're like, all right, I got to get rid of this, and then also this thing somehow. So I see the dx here, and I got this x squared plus 1, and so there's an x squared and the number here. And so you just got to think like, oh, are these really the same? Almost. Hopefully it's not too bad to see. Yes, you can just factor a 3 out of here, and you do end up with your x squared plus 1 dx. What do we always do? This extra number, get it out of there. Okay, so du over 3 is x squared plus 1 dx. So x squared plus 1 dx becomes just du over 3. And would you look at that? Can I get any easier? I guess yes, but not too much. Do your antiderivative. 1/3. Add 1, divide. Okay, we've got 1/15. And then I'm going to even combo step here, right? I'm combining these numbers and I'm going to plug back in for x. If you want to get a little fancy, you can do a couple steps all together. You don't need to be too fancy, but if you want to, and there you go. All right, let's keep going. Okay, sine ln x. So let me bring this one up. All right, so again, functions, log, trig, oh no. I'm just going to look for an inside and an outside. That's it. Like, what's inside? Well, I got c sine here, and then natural log's inside. So just give it a shot. Take the derivative, 1 over x. Go back up here. This couldn't have worked, right? Like, look at this. Oh, dx and an x on the bottom. Okay, it worked perfectly. Let's go. Integral, right? Sine, natural log is u. X on the bottom, dx. That's just du. And look at that. That's it. That's the whole integral that's left. All right. Derivative of this is negative cosine u. Okay, plus c. And then let's go back to boom. All good. There you go. So just find the function inside another, give that a shot as your u, take the derivative, and just see what happens. And your goal is to get into this nicer function in here to take the antiderivative of. Okay, let's keep going. All right, so we have now gotten to talking about definite integrals. Okay, so 2 methods here for this. Method 1 is do the integration, okay, and then go back to your original variable. Because remember, you're switching into u's, right? So do the u sub, do the antiderivative just like we did, switch back to u's, apply the bound. Or, and we'll do it both ways, you can actually change these limits from t's into u's and just use the new limits and keep everything in u. So those are the 2 ways. Let's try them both. Let's get down here, zoom in a little bit more. All right. Okay, so we're going to treat this to start like it's just from before. Find a function inside another. So, okay, I see just really only one thing here. This inside to the 50th. So let's let u equal 3t minus 1. du is 3 dt. I don't have a 3 out here, so we know we can get rid of that. So du over 3 equals dt. So over here, take all these over here, and then do the substitution. Okay, so we've got u to the 50th, and then dt becomes du over 3. Awesome. Now, here's the thing. The bounds currently are t equals 1 and t equals 2. So let's show the switch. So if you want to stay in u's, watch what you can do. When t equals 0, well, what's u going to equal? Only if I had some formula that connected t and u. This would be so easy. If I just had it's right here, I'm pointing at it. Yes. So watch what we can do. We've got t equals 0. That's u then equals 3 times 0 minus 1, which is negative 1. Boom. And then we've got t equals 1. U equals 3 times 1 minus 1. That's 2. These are now u bounds. So I can just do this like, I know how to do this integral. So let's do it. Let's move the 3 out. So 1/3 integral from -1 to 2 u to the 50th du. We're going to add 1, divide, and then remember we're going to plug in 2 first and then -1. Remember, top, then bottom. Okay, so let's go down here and do that. So that's 1/3 2 to the 51st over 51 minus -1 to the 51st over 51. This is going to be a ginormous number. 2 to the 51 is very big. So I'm not going to try to do that in my head, obviously. Let's see if my phone calculator can even do it. 2 to the 51. Wowzer. We're going to leave it like that because that is a very big number. There you go. So that's it. That is how we do it. All right. So recap. U sub. Okay, just like we were doing. Switch the bounds to use, and then this problem we know how to do. We're all good here. Now the other way you can do this, right, is leave off the bound switching, and at this point, so method number 2 is we're going to take this and we're going to copy it over here. Okay, copy it over here, and we're at 1/3 u to the 51 over 51, and to some bounds, right, that are t bounds, but we're in use, so we're just going to leave them for a second. Do the substitution. Well, actually, this is really, right, what was u? 3t minus 1. So really, this is 3t minus 1 to the 51 over 51, and that was from 0 to 1. Plug your 1 in, plug your 0 in, and you're going to get that. So do it either way, doesn't matter to me. All right, let's keep going here. So again, we have a function and another function inside. So let's do our process. U is x squared. Du is 2x dx. I don't see a 2 in here, so we're going to get that 2 away. Divide it, divide it. Okay. And then we're going to, now again, you have the choice of, doing this integral and then, switching the bounds right away, or subbing back. So let's do the second method since we did the first method the first time. Okay, so let's do the substitution. So we've got the integral of, okay, and then remember, cos of u, and then dx and x right here becomes du over 2. Okay, remember I've got these bounds here, which we're not changing, so I'm just going to leave them. You can just leave them off, but I'm just going to put little stars for now. Okay, so we can do this one. So the antiderivative of cosine is sine. We've got our 1/2. Okay, and then remember, we've got these bounds we have to do. Now instead of changing the bounds to u's, I'm just going to change this back to x's. So I'll move that over here. Let's go over there. So that's 1/2 sine x squared from 0 to root pi, which will be equal to 1/2 sine root pi squared minus sine 0, and that's squared inside. Okay, so then 1/2 sine pi, because the square and square root will cancel. So remember, sine pi, draw your little circle. Here's 0, pi over 2, here's pi. All right, well, sine of pi is 0. Sine of 0 is 0, and we get 0. All right, so there you go. All right, next one. Okay, so again, looking kind of complicated maybe, but again, just can I find a function inside another function? So let's try it. I see a cosine, okay, whatever. Then I see sine, and oh, there's a sine inside. So take your sine x. What's the derivative? Cosine x. And then just try the substitution. Integral sine of u. And then remember, we've got dx and cos x, and look at that. That just becomes du. Yeah, not too bad. So antiderivative of that is negative cosine u, right? And then remember, we've got these bounds here that we have to do. And so what we'll do then is we'll plug back in for x. So negative cosine sine x from 0 to pi over 2. Okay. And then we can plug in. So let's go down a little bit more. Negative cosine of, and then we're going to plug pi over 2 in here. Cosine of sine of pi over 2 minus cosine of sine of 0. Okay? So then sine of pi over 2 is 1. So that's 1. And sine of 0 is 0. So this is negative cosine 1 minus cosine 0, which ends up being negative cosine of 1, which you can plug in a calculator to get a decimal, but we're just going to leave it like that. And then cosine 0 is 1, so negative, negative. There you go. Whenever you get something like this, you can plug it into a calculator, do some rounding, but you know, it's more correct to just leave it in this form. So okay, let's keep going. All right. So we've got this one here. Now let's try it out. So again, function inside another. U equals, okay, x minus 1. Du is just 1 dx. So let's just see what happens. Do the substitution. So, and we'll, again, for this time, we'll just practice again. We'll just ignore the bounds for just a moment. So get the integral square root of u. Okay, and now here's the tricky part. Because dx and dx, right? So that dx just becomes du. But I haven't dealt with this x yet, right? There's this extra x and I haven't done anything with it. Here's where we got to be a little tricky. Again, I want to turn x's into u's. If only we had a formula that combined x's and u's together. Oh, we do again. Okay. So x minus 1 was u. But remember, this is an equation. I can do any algebra step I want on this, right? As long as I do it correctly. So we can rewrite this so that we have something just for x. So let's do it. I'll keep it in green. So let's go over here. I need some way to just get x by itself. So I'm going to add 1 to both sides and get u plus 1 is x. Okay, so then anytime I see an x, I can put a u plus 1. So really, that's where we were. Really, this becomes integral of u plus 1 times square root u du. All right, let's multiply that out and kind of simplify this a little bit. It's the integral. Now remember, these two hit, u to the 3/2. These two hit, u to the 1/2 du. And again, at this point now, it's up to you. Do you want to switch the bounds? Do you want to plug back in for x? Let's just switch the bounds this time so you can see the practice. So the bounds were 1 to 2. So then when x equals 1, u is equal to 0. Just plug it in. And then when x equals 2, u is equal to 2 minus 1, which is 1. That's not too bad. Now we have u bounds. Okay, let's do our antiderivative. Give myself some more space. Add 1 and divide, right? Add 1. So we get 3/2 and divide. And then plug in your bounds. So we're going to plug 1 into here. We're going to get 2/5, and these are nice numbers, right? 1 to any of these powers is just 1. So these all just become 1. So really the first piece is just this, minus, and then we're going to plug 0 in. 0 to any of these powers is just 0. All right. So then, you can put this in a calculator if you want, but we can get up to 15ths here, right? So this will be 6/15 plus 10/15, which gives me 16/15. But you could just do that in a calculator if you want to. Okay, let's keep going. All right, so we've got one more, and we are going to be doing a word problem here. So let's read through it. A bacteria population starts with 400 bacteria and grows at a rate of R of t equals 450.268 times e to this negative power. So stop right here. What is this growth rate telling you, right? E to a negative power. What is e to a negative? Just make it simpler on yourself. E to the negative t. You don't get rid of some of this stuff. Remember what this looks like. This is decreasing. Looks something like that. We don't have to be perfect, but it's something like that. So, okay, just thinking. Okay, so it starts with that and grows at a rate of 450 times, and some junk, times e to the negative 1.1256 t bacteria per hour. How many bacteria will there be after 3 hours? So, what do we know? This is a growth rate. Growing means change. Okay, so we're changing. So think about what we just talked about in 5.4. I know how something's changing. How do I use that to learn about the thing itself? Well, we integrate. Remember, we integrate. We know how to do this. We do the integral. So we integrate the change, 450.268 e to the negative 1.12567 t. We integrate the change over the time period. So this is in terms of hours, okay, per hour. So we go from 0 to 3. Awesome. We got this. So you got to make the connection. Change. If we know change, this is 5.4 idea, we can use an integral to add up, in a sense, all of that change to see what will happen. So let's go through and do this. First things first, let's just move this number out here. Integral from 0 to 3, e to the negative 1.12567 t dt. Okay. All right, so it looks like e to the t almost. It's just that, there's this extra power up here. Like, what do we do? Well, that kind of looks a little bit to me like a function, not a very complicated one, but that's okay, a function plugged into e. So, get your u. That's what's upstairs here. That's making it not quite just e to the t. Do our du, which this isn't a too tough a one, right? Okay, but this number is not out front here, so what have we been doing? Divide. Let's divide it over. Okay. And then what we have to do is we've got to do our substitution. So this is going to equal 450.268. And now notice there's bounds here, so it's it's totally up to us kind of what we want to do with the bounds. Do we want to switch back to t, fix the bounds? What do we want to do? So we're going to go through here, do the substitution first. Just focus on that. This is e to the u. Oh, that's nice, right? And then dt right here becomes du over that number. you're going to notice this as a common theme. If all you're doing here is multiplying a number by the variable, that's like the only change, you'll just consistently see this number pop out in the divisor. Like, so you'll see that happen a lot, and you'll be able to go through these a little bit quicker when you notice that. They just keep popping out down here. Okay, so let's pull this number out. So this is 450.268 over negative 1.12567. Oops, I included an extra t in there somehow. I don't know how that got in there. Okay, and that's the integral of e to the u du, which we know how to do that. That's just e to the u. So we get this number, which we're going to plug into the calculator now so we don't have to keep writing stuff. You know, really we should be waiting to the end, but it's not too big of a deal. Divided by negative 1.12567. And I end up getting negative 400 on the dot. Integral e to the u. Okay, again, e to the u, the antiderivative is e to the u. So this is negative 400 e to the u. Now, bounds. The bounds used to go 0 to 3, but that was t, right? So if we want to stay in u, we have to change the bounds. So over here with the bounds, let's say, well, when t equals 0? Well, that's easy. U is 0. Cool. When t is 3, not quite as nice. U is equal to negative 1.12567 times 3. Okay, which let's plug that into a calculator and see what we get. Negative 1.12567 times 3. This gives me negative 3.37701. So that goes up here. 0.37701. Okay, and then let's give ourselves a little more space here. And that's equal to negative 400 times, plug in, e to the negative 3.37701 minus, plug 0 in, equals negative 400. Now, we're going to just plug this into the calculator now and kind of try to get a guess at what's going on here. So e to the power negative 3.37701. All right, that's 0.3415 minus e to the 0 is 1. So minus 1. And then we're going to multiply that by negative 400. Gives me 386.34. So that's my population. All right. So there you go. We've got it. So lastly, there's a little bit more in the book about symmetry in integrals. It's a pretty interesting thing to kind of check out, and it's a valuable thing, later on to just kind of have that in your, in your tool bag, that there are some integrals that you can simplify greatly with this idea of the function symmetry. So check that out. I'm not going to test you on it, but it might be something that'll be useful at some point that might get a little use out of. All right. So any questions, of course, ask, let me know, and I'll see you in the next video.